Hello everyone, I am Zhou from the University of Oxford. Today I'm here to present our paper Divide, Conquer, and Combine, which is a new inference strategy for probabilistic programs with stochastic support. Let's kick off with an example to see what does stochastic support mean and why they cause problems. Suppose I have collected some data that I want to model for future prediction. However, it may contain one mixture, two mixtures, or more, so I decide to use an open mixture model where the number of the mixtures k is unknown as well as the center of the mixtures mu 1 to k. Note that this model has a stochastic support since the number of the total latent variables depend on k. My goal is to learn the posterior for future prediction. Throughout my talk, I will use pi x for the posterior distribution, gamma x for the unnormalized density, and z for the normalizing constant. Universal probabilistic programming systems provide a good way to encode model as program. Especially, they allow the user to define many non-standard models, such as models with stochastic support. The system further provides automated engines to perform inference in these models, but doing so successfully is extremely challenging. Take our mixture model as an example. We can easily define this model in a particular PPS as shown in the pseudocode. I can then call the automated inference engines such as MCMC or variational inference, and the system will return me the estimate of the posterior distribution pi hat. Provided this estimate, I'm now ready to do prediction. However, if you look at the plot lower right here, they don't make sense at all. The black line is the KDE plot of my data, and the green and brown lines are the posterior predictive distributions from the estimates of MCMC and variational inference respectively. Neither of them seem to capture the pattern of my data. In fact, up to our knowledge, we did not aware of any universal PPS inference engine that is able to deal with this ostensibly simple model. This is the key motivation of our work. The central question we're addressing today is how to perform inference properly for the models with stochastic support. Before we introduce our solution, let's first review the fundamental reason why existing methods struggle. We argue that for many inference methods, MCMC in particular, the key bottleneck is the need to transit among different configurations. Let's have a look at the two-dimensional mixture model for a better exposition. As above, we have the cluster number k and cluster center mu's as the latent variables. When we use one single MCMC chain to approximate the posterior, the chain not only needs to move properly with a fixed configuration, but also needs to transit to a different possible case. Imagine that we start the chain from the configuration of k equals to 1, and the initial sample is at mu1, 0. Suppose the first few steps remain in k equals to 1 until the kth iteration where we reach mu1t. For the next step, suppose the proposed sample of k is 2, which means we try to transit into a new configuration where we have an extra cluster. This follows by proposing the movements of mu's. Mu1 is straightforward because it exists before, so we propose the small movement and move to mu1 prime. However, mu2 is a new variable that we did not have before, so we randomly sample from its prior. As you can see here, it is difficult to land in a region with high posterior mass for the new mu's when configuration changes. Therefore, it is very likely that we will reject this movement. Even worse, our chain may get stuck in k equals to 1 forever and miss the configuration of k equals to 2. Because it is so difficult to transit among different configurations properly when the support is varying, can we instead break the problem up and solve each sub-problem respectively? For example, in the open mixture model, we might want to break the overall model into submodels with fixed k, and then we can perform inference in each submodel with a fixed set of variables before we stitch the results together. By doing so, we divide the overall problem into a series of simpler sub-problems, conquer each sub-problem, and combine them together. We therefore formalize this idea into our framework: divide, conquer, and combine. At a high level, divide, conquer, and combine works by dividing a program or model into sub-programs, conquering each sub-program before combining the results together. If we think back to our open mixture model, this means that we divide the model into multiple sub-models with fixed k, like k equals to 1, k equals to 2. We conquer each submodel by running inference in the submodel respectively, and then we combine the results together at the end. Before we introducing more details, you might wonder, what does divide a program mean? Here is an example. Intuitively, a program may have multiple paths, where each path is a unique sequence of executable statements. The program here defines a branching model with 2 paths. When we execute the program, we start at the first line and sample the variable z0. Suppose it is minus 0.5. At the second line, depending on its value, we either go to the true branch or false branch. Since minus 0.5 is smaller than 0, we go to the true branch and draw the variable z1 being minus 6.2. We then evaluate the likelihood at line 4 before we finish. In this execution, we record the program path by the address of the encountered random variables, which is line 1 and line 3. We have the draws of all the random variables being minus 0.5, minus 6.2, and we have the execution trace being the address value pair sequence. If we execute the program again, we might go through a different path. Suppose z0 is 1.1 now, which means we will enter the fourth branch and draw the variable z2 and z3. This gives us a new path through line 1, 6, and 7, the new draws being 1.1, 4.5, and 5.6, and a new execution trace. Probably you have figured out the rules already. We now formally define a path of a program being the address sequence of the encountered random variables, and the draws as the sequence of the values of the random variables, and the execution trace being the address value pair sequence. We can now use the path to define a straight line program. Intuitively, a straight line program is a part of a program following a specific path. For example, we have 2 straight line programs, A1 and A2, in the branching example as we have seen before. The first component of DCC, divide, is responsible to divide the overall program into multiple straight line programs with unique paths. We can think of dividing the branching model program into true branch and false branch, or dividing the earlier open mixture model into submodels with fixed k. Breaking the problem up makes an easier inference problem later. Now, at the second step, conquer, the main task is to perform local inference restricted to each straight line program AK. Formally, we want to estimate the local posterior pi k of each straight line program AK. Its unnormalized version, gamma k, is defined by the overall joint density gamma restricted to a subspace mathematical xk, and zk is the local marginal likelihood. Take the earlier mixture model again. Pi k here means the posterior of the submodel with k being fixed. The advantage of running inference locally is that we are now in a fixed support regime where many conventional inference methods can be performed efficiently. As a result, we should be able to obtain a more accurate overall estimates. In the end, we combine all the local results according to our derivation and form the unified estimates of the overall posterior. In particular, this requires the estimate of the local posterior and local marginal likelihood. Let's recall what we have gained in this setup. First of all, we break the problem up into a series of simpler sub-problems with fixed support. By doing so, we are able to obtain more accurate estimates. Last but not the least, this also enables us to allocate computation resources in a smarter way, since some straight-line program may have higher posterior mass, which we want to estimate better. Let's now have a look at a few examples to see the performance of DCC. The first one is the earlier open mixture model. We first look at the convergence of the marginal likelihood. Here, the y-axis is the squared error of the marginal likelihood estimates, and the x-axis is the computation cost. We compare DCC against importance sampling and an MCMC variant, RMH. Note that RMH does not produce the estimate for marginal likelihood directly. So what we do here is to generate importance samples from RMH to estimate its value. As we can see from the plot, DCC substantially outperformed the baselines. You may wonder why our main baseline is importance sampling. This is because when we encounter new configurations, many sophisticated methods redraw things from the prior, which essentially fall back to importance sampling. We further investigate the posterior of the cluster number k over 15 independent rounds. In particular, we look at the posterior of k being 5, which is the number of the clusters when generating the synthetic data. As we can see in the bar plot, DCC produces the most accurate and consistent results. We then use an extreme prior of the previous mixture model to test the ability of DCC to discover submodels with high posterior mass but low prior probability. The data have 5 clusters, but we set the prior of k to be Poisson 90. Here we're showing the visit history of each submodel between RMH and DCC. It is clear that RMH mostly gets stuck in the initial submodel. DCC, on the other hand, starts from the submodel corresponding to around 90 clusters, which is close to the prior, and is able to discover the submodel of 5 clusters which contain the most posterior mass. Being able to discover submodels is a key reason why DCC can perform accurate inference. We can do more interesting things as well, such as introducing a grammar over functions and then perform the inference over the space of the functions. Here, the blue dots are the training data and the orange ones are the test data. The gray lines are the posterior samples of the inferred functions. As you can see on the left, DCC is able to fit the data way better than the baselines. Please do check out our paper for more details. I hope you're excited to know more about our method now. The takeaway message of today is that models with stochastic support are difficult. Treating them as a whole is very inefficient. DCC instead divide the models into submodels with fixed support, conquers each submodel before combining the results together. That's all. Thank you very much for your time.